Lesson 7.6 is about proportional lengths. Okay, how this works is this. I have two segments here, segment AC and segment DF, and I've divided up AC to between AB and BC by putting a point B in the middle, and I've done the same thing with E between D and F. Well, not in the middle, but somewhere in between them. So what we can say is if the ratio, let's go red here, if the ratio of AB to, erase that. If the ratio of AB in red to BC, I'll put in blue, is the same as the ratio of DE to EF, in other words, if those two segments are in proportion, then AC and DF are what we call divided proportionally. Okay, so I think that we've been working a lot with proportions, and we can understand that. So let's put in some numbers. Let's say AB is 3 and DE is 6, and let's say that BC is 8, and we don't know what EF is, so we could write a simple proportion to figure that out. So I could say between the two figures, so AB to BC, so 3 is to 8 as 6 is to x. Okay, and so to solve for that, 3x is certainly equal to 48, and so obviously x is equal to 16. And we could see that quite easily just looking across. If we just look here, 3 times 2 is 6, and 8 times 2 is 16. So proportions work, remember, horizontally. 3 is to 6 is 8 is to 16, as well as vertically. So those are proportional lengths. So the first theorem in this lesson is the triangle proportionality theorem. And what this says is that if you have a segment that goes through like the middle of a triangle, like this, and it happens to be parallel to the third side, and it intersects two of the sides, that it divides the triangle, those two sides of the triangle, proportionally. In other words, the ratio of the 6 to the 3 will be the same as the ratio of this 3 is to this 2. And that's not right. Can you find my mistake? Well, it's that it doesn't work. Because I accidentally wrote a 3 here instead of a 4. So that should be 6 to 4. And this should be 6 to 4. Okay, now we fixed it. 6 is to 4 as 3 is to 2. And looking across, 6 is to 3 as 4 is to 2. Okay, that's the triangle proportionality theorem. Okay, and a corollary to the triangle proportionality theorem is that when we have transversals lying across parallel lines, so what I've got here is I've marked these are 3 parallel horizontal lines, and I have a blue transversal and a green transversal. Well, it divides, those parallel lines divide every transversal proportionally. So as an example, if this piece here on the blue transversal is 3 and this piece is 2, and even though this isn't drawn to scale, if on the green transversal this piece was 6, then the piece over here would be 4. So I would have 3 is to 2 as 6 is to 4. These would be proportional. And of course, looking at it horizontally, 3 is to 6 as 2 is to 4. So those transversals are divided proportionally. So next is the triangle angle bisector theorem. And what this says is that if we have in a triangle an angle bisector, so let's say that these two angles here are equal. So I can see that angle D has been bisected by segment DB. If that's the case, then what happens is this. It divides, this bisector at point B will divide the other two sides proportionally to the sides that are adjacent to them. So the AB will be in the same proportion relative to side AD, and as BC, so this blue side BC is relative to the length of DC. So basically, the ratio of well, let's fill in some numbers and look at this. Let's say that AB is 4. I'll do this in red. Let's say that AB is 4 and AD is 5, and then BC will be 6, and let's say we don't know what DC is. We'll make that X. Okay, and what I'm saying is that the ratio of red to blue of 4 to 6 is going to be equal as the same ratio of red to blue of 5 to X. So let's go red. 4, the side that's 4 is to the piece that's 6. So I just looked at this one. Its ratio to that side is going to be the same as the ratio of the red piece over here, 5. This leg of the triangle adjacent to the AB is to X. So I just went as 6 is to this X here. So then that's easy enough to solve. 4X is 30, and so X is 7.5. Okay, so 4 is to 6 as 5 is to 7.5. 6 is 1.5 times 4, and 7.5 is 1.5 times 5. Okay, so that's the angle bisector theorem for a triangle. So let's look at a few examples. First, this is an example of using the triangle angle bisector theorem, because at the top here, I have an angle that's been bisected. So what I know is that's going to divide these two bottom pieces into sides that are proportional to these two other sides. So I could set up a proportion here, but I don't know what to call the two bottom pieces. So I know the whole, across the whole bottom is 10, so I'm going to call this piece X, and if that's X, then this other side of it will be 10 minus X. So I can say that X, the ratio of X to 10 minus X, will be the same as the ratio of 9 to 6. Or you could say the ratio of X to 9 will be the same as the ratio of 10 minus X to 6. Either way. Anyway, cross-multiplying to solve this, we get 6X equals 9 times the quantity 10 minus X. So 90 minus 9X. So 15X is 90, and X equals 6. So that means this piece is 6, and this other piece will be 10 minus 6, or 4. So an example of the corollary about parallel lines. Let's say I have these. Let's say these are all three parallel lines cut by two transversals, and so we know that those transversals will be divided proportionally. So I can look at it this way. I can say, oh well, the ratio of 10 to 15 should be in proportion to, or the same as, the ratio of 14 to X, if I want to find that missing piece, X. So 10X equals 15 times 14, which is 210, so X is 21. So this piece here is 21. Okay, let's look at the triangle proportionality theorem again, and we know how the top, on this case, because I have a triangle with a segment that's parallel to a third side, I know that these two legs, this one, this piece here, the ratio of that top to the bottom is the same as the ratio of the top to the bottom. But I also know that the top to the whole is the same as the top to the whole, or the bottom to the whole is the same as the bottom to the whole. So I can write a proportion and solve for X just knowing that the ratio of X to 14. So the top part to the whole part is equal to the same as the ratio of the top part, 6 to the length of 16. So 16x equals 6 times 14, which is 84. So x is equal to 84 over 16, which simplifies to 21/4. Okay, or, if I wrote this as a mixed number, I could say 5 1/4. Okay. Okay, another way I could find x is I could use the bottom to the whole. Let's just say that I know if this whole left side is 14 and the top part's x, that the bottom part is 14 minus x. And on the right side, if the whole thing is 16 and the top is 6, I know the bottom is 10. So I know bottom to whole is equal to bottom to whole, so I could set up the ratio, the bottom segment of 14 minus x over 14 is equal to the bottom segment of 10 over 16. And I might want to take this 10 over 16 and simplify it to be 5 over 8, so I don't have as big a numbers to work with. So then I can cross multiply. So I get 8 times the quantity, 14 minus x, which is 80 plus 32, which is, we'll just write it like this right now. 14 minus x equals 14 times 5, which is 50 plus 20, which is 70. Okay, so let's see, 8 times 14, this is 112 minus 8x equals 70. And if I simplify, add 8x to both sides, subtract 70, I'll get 8x equals 42. And x is equal to, once again, 5 1/4, just like when we solved for it in the last example. So just to show that these proportions work all ways, I can still just go back to top to bottom is going to be proportional to top to bottom. So my top segment on the left of x to the bottom segment of 14 minus x is proportional to, will be the same ratio as the top of 6 is to the bottom of 10. So I think I'll simplify the 6 over 10 to a 3 over a 5, and then we can cross multiply. 5 times x equals 3 times the quantity 14 minus x. So 5x equals 42 minus 3x, and there, just like in the last problem, we'll get 8x equals 42. So still, x is equal to 5 1/4. Okay, so this just shows this triangle's divided top to bottom equals top to bottom, top to whole equals top to whole, or bottom to whole equals bottom to whole. And that's it for proportional lengths.